Lab 1, Constant Velocity Motion by kguzdial. To find an object in your everyday environment that moves at a constant velocity. To capture an object moving in constant velocity motion, I filmed a soccer ball rolling across a wooden floor after being pushed from the negative x-axis to the positive x-axis from time t equals 0 to t equals 1.208 seconds. I used the center of the ball as my point of reference to find the change in x per frame. This is the data gathered from the video. According to Newton's second law, the net force is the sum of the forces, or pushes and pulls, in a system. To calculate the final velocity, find the initial velocity plus the net force divided by the mass times the change in time. The momentum principle, translated from Newton's second law, states that the change in motion equals the net force times the change in time. To calculate velocity, I found the change in position over the change in time after one frame. To create an accurate model of the soccer ball's motion, I tweaked a code written in Python. First, I changed the ball's mass to that of the soccer ball, 0.45 kilograms. Next, I changed the position to the ball's initial position. Then, I changed the ball's velocity to the velocity I calculated in a previous slide. The video started at time t equals 0, so I left t equal to 0. For the other initialization, I left delta t equal to 0.01, even though my change in t per frame was 0.042, simply to get a more accurate prediction. To store the data calculated in the Python code, I uncommented several lines that would output a CSV file of this data. The end time in the movie was 1.208 seconds, so for the loop in the code, while t is less than 1.208, the ball's velocity will increase by the initial velocity plus the net force divided by the mass times the change in time. The ball's position will change by the ball's initial position plus the ball's new velocity times the change in time. The new time will be the initial time plus the change in time. Since the ball is supposed to be moving in constant velocity motion, the net force is 0. Now, running the Python code should show us an accurate model of the soccer ball and tracker. Using the output CSV file, I compared the data from tracker to the data from the Python code in a line graph where the x-axis is time and the y-axis is position. You can see clearly that the two lines are not equivalent. There are many possible reasons for this. One reason could be that the force was not actually 0 because of friction. Another reason could be that I did not use a short enough or correct part of the movie of the soccer ball, where the ball is actually moving with constant velocity motion. In addition to these possibilities, I gathered that although the ball was moving towards the positive x-axis, the ball was also rolling slightly towards the positive y-axis. However, even after slightly changing the angle in tracker, the graph still produced the same results. The ball did not move in constant velocity motion. Perhaps because the ball did appear to move slightly towards the positive y-axis, flipping the coordinate system may have produced similar results. The ball also did not experience 0 net force. The pushes and pulls did not cancel each other out.